Okay, this YouTube is about gravitational potential energy, which I will often refer to as GPE. So we learned about kinetic energy in the last YouTube, and there is energy associated with moving a mass up or down. So to motivate that idea, let's consider a mass m close to the surface of the Earth, and I've this dot down here represents the mass of the Earth. And let's say we um, move this at constant velocity upwards, an upwards displacement of delta y in the vertical direction. And so in the process of doing that, I put my hand on the mass, and so there's an upwards f of h on m, and there's a downwards mg. And if I'm moving this up at constant velocity, the sum of these two forces is 0, which means the magnitude of f of h on m is mg. And so therefore the work done by the hand on the mass is mg times delta y, and since both of these are in the same direction, that's bigger than 0. On the other hand, if we do the same thing but we lower the mass m a displacement delta y, same scenario though in terms of the f of h on m, since we'll lower it with constant velocity, and so these two forces will be same magnitude but opposite direction. And in that case, the work done by the hand on m is minus mg delta y. It's negative here because the displacement is downwards, but the force of the hand on the mass is upwards, and so theta is 180. They're anti-parallel, and you have to keep a minus sign. So to encapsulate this definition, and in order to keep account of the gravitational potential energy, what we do is we define gravitational potential energy to be m times g times y. Mass times the acceleration of gravity times y, the height above the ground. And it is important to understand that this energy is shared between little m and the mass of the Earth. And so the system you have to use if you're doing this is the mass m and the mass of the Earth together. So you'll notice the same system concept that we introduced in discussing impulse and momentum is also here in energy. One caveat to this definition of GPE is it's good only if you're relatively close to the ground, and that is if the distance above the ground is small compared with the radius of the Earth, which, as you will recall, is some 6,400 kilometers. And so you can go kilometers above the surface and still have this formula be pretty good. When you start getting to hundreds of kilometers, it becomes a little bit more touchy. And when you get to thousands of kilometers, it's less viable. The reason for that is the inverse law of gravitation says that the force gets less and less as one goes up, and the scenario for this gravitational potential energy calculation is that the force is constant and equal to mg. So that's why this caveat is there. Let's take an example. Let's say we have, we'd like to find the gravitational potential energy of a 5 kilogram mass that's 2 meters above the ground. And so we would take the mass, 5 kilograms, multiply by the acceleration of gravity, 10 meters per second per second. I am using easy numbers here. 2 meters above the ground, and that indicates that this mass has a 100 joule gravitational potential energy.